This body of water is here by accident. Let me explain.
Once hailed as a desert paradise, in the 20th century, the Salton Sea became one of America's greatest environmental catastrophes. For decades, its toxic waters and collapsing ecosystem masked something hidden, something far more valuable than anyone imagined.
There is truly a miracle in the desert. A whole new outlet for the crowded millions in big cities.
But lately, beneath the salt, the bones, and the dust storms, scientists have discovered a force with the power to reshape global energy. This is how a fading man-made lake became the epicenter of a potential energy revolution. What lies beneath is not just unexpected, it's mind-blowing. The accidental sea. In the early years of the 20th century, the Imperial Valley was a harsh, unforgiving desert, carved from arid sands and dotted with scrubby plants that barely survived the scorching sun. The Colorado River, miles to the east, was both a blessing and a challenge. Its waters promised life to farmers willing to tame the wilderness, but controlling this mighty river was a daunting task. In 1905, an engineering disaster forever altered this landscape. An irrigation canal designed to divert Colorado River water to parched farmlands cracked under pressure. The breach was catastrophic and unexpected. Torrents of water surged through the desert basin, sweeping away dry soil, carving channels, and flooding low-lying areas with relentless force. For nearly 2 years, the river refused to be tamed, relentlessly pouring into this closed basin with no natural outlet. What was once an empty desert basin quickly transformed into a sprawling, shimmering inland sea. The water expanded over 350 square miles, swallowing farmlands and altering weather patterns. This new body of water, soon named the Salton Sea, became California's largest lake. But unlike the natural lakes carved by glaciers or rain-fed rivers, the Salton Sea was artificial, born of human error and natural forces colliding. For a brief, dazzling moment, the Salton Sea seemed a blessing. The surrounding area blossomed with promise, and in the 1950s and 60s, it became a magnet for vacationers and tourists. Resorts dotted the shoreline, boats skimmed across the water, and families flocked to its beaches. It was a desert oasis, a glittering jewel amidst the sands. But beneath this surface idyll, the sea was a fragile and volatile system. Without an outlet, salts and minerals brought in by irrigation runoff began to accumulate. The relentless California sun and the region's intense heat triggered rapid evaporation, leaving behind a growing concentration of salts, slowly turning the lake's waters into a briny, toxic stew. Pollutants from agricultural runoff, pesticides, fertilizers, and untreated sewage also began to build up. The chemical cocktail transformed the water's composition, making it increasingly inhospitable for life. Slowly, the paradise began to crumble, unseen by the tourists who continued to visit. Beneath the shimmering surface, a quiet transformation was underway. Layers of sediment settled, trapping pollutants and creating pockets rich in minerals yet lethal to wildlife. The sea's bottom was shifting in ways few understood, as geothermal activity from deep underground pulsed faintly, stirring the brine in subtle, powerful ways. Unknown to the world, the Salton Sea was not just dying, it was evolving. Death on the shoreline. By the late 1970s and early 1980s, the first signs of the Salton Sea's collapse became impossible to ignore. Dead fish began to wash ashore in alarming numbers, carcasses bloated and lifeless, a haunting testament to the lake's poisoned waters. Species once abundant, like tilapia and corvina, struggled to survive in the increasingly acidic and saline environment. Birdwatchers and ecologists noticed a far grimmer sign. Birds were falling from the sky. Migratory species using the Salton Sea as a vital stopover during their journeys were dying mysteriously. Scientists quickly linked the phenomenon to the contaminated waters, where heavy metals and pesticides had accumulated in the food chain. DDT, selenium, and other toxic elements had reached lethal levels. The birds ingested contaminated fish or water and suffered devastating effects, including neurological damage and sudden death mid-flight. The once vibrant shoreline was now a barren wasteland. The receding water exposed vast stretches of cracked white salt flats mixed with bones and shells, the skeletal remains of millions of fish and other aquatic life. Winds whipped over these exposed lake beds, sending clouds of toxic dust and particulate matter into the air. These dust storms posed a serious public health hazard, contributing to respiratory illnesses in local communities. Scientists who monitored the sea's chemistry grew increasingly concerned. Measurements revealed mineral concentrations, far exceeding those typical in natural lakes. Salinity levels had surpassed that of the ocean, but it wasn't just salt. Layers of brine, enriched with magnesium, lithium, boron, and other rare minerals, settled in pockets at the lake's depths, creating a strange and hostile underwater world. Around the perimeter, geothermal wells, natural hot springs, and man-made drilling sites pulsed with unexpected heat and strange chemical signatures, and churned, releasing gases and minerals that altered the lake's chemistry in unpredictable ways. Scientists speculated that the Salton Sea was situated above a geothermal hotspot, a zone of subterranean activity linked to tectonic movements along the San Andreas Fault. And given the fault's constant movements, the threat of a catastrophic spillage of waste materials into the ecosystem seemed increasingly more likely. The fault below. Beneath the shimmering, often deceptive calm of the Salton Sea lies a simmering geological tinderbox. Running directly underneath this vast saline basin is the southernmost stretch of the San Andreas Fault, one of the most notorious fault lines not just in California, but the entire North American continent.
Now here in California, you have dangers from a number of different kinds of earthquakes. The major danger is from the earthquakes on the San Andreas Fault system.
This fault has been the source of some of the most devastating earthquakes in recorded history, a restless scar marking the relentless grinding of the Pacific and North American tectonic plates. For centuries, scientists have monitored the region, aware that its seismic story was far from over. The Salton Sea sits precariously atop this volatile fault zone, a place where Earth's crust is stretched, squeezed, and fractured. What was once considered merely a quirky geological feature, a lake formed by a century-old irrigation accident, had become a focal point of intense scientific scrutiny. Seismographs placed all around and beneath the sea began recording a startling pattern: micro-earthquakes. These tiny seismic events, often imperceptible to humans, pulsed with a strange rhythm. But what caught researchers' attention were clusters, swarms of microquakes that flared suddenly, like irregular heartbeats in the Earth's crust. These swarms weren't random, they seemed triggered, linked by some unseen underground force. This wasn't typical fault friction, or the slow creep of plates sliding past each other. Instead, the tremors hinted at something deeper and more complex. Thermal anomalies appeared, pockets where heat surged unexpectedly from the Earth's interior. Tectonic stress built unevenly, with some zones relaxing while others tightened, as if the fault was being squeezed and pushed by hidden pressures. The Salton Sea's fault was awakening in a way that challenged conventional understanding. It wasn't just the mechanical movement of rock on rock. Something beneath, an enigmatic force, possibly connected to the region's unique geothermal activity, was stirring tectonic unrest on a scale and in a pattern never before witnessed. Geologists, volcanologists, and seismologists began converging on the area with new urgency. Advanced seismic imaging revealed shifting magma chambers, deep reservoirs of superheated water, and pressurized gas pockets trapped in layers below. The Salton Sea had transformed from an ecological curiosity into a geological anomaly, a rare window into the restless dynamics of the Earth's crust. The implications were chilling. An earthquake here, amplified by geothermal forces, could trigger disasters far beyond the Salton Sea basin. Fault ruptures might propagate northward, threatening urban centers like Palm Springs and even Los Angeles. This was a natural pressure cooker, and scientists worried that the balance was precariously close to tipping. Mud pots that move. South of the Salton Sea, nestled near the sleepy desert town of Nyland, California, something extraordinary was unfolding, and it wasn't something anyone could have predicted. The region is dotted with geothermal features known as mud pots or mud volcanoes, bubbling cauldrons of boiling water, thick mud, and escaping gases like carbon dioxide and methane. These strange, otherworldly pools have existed for decades, shaped by the intense heat and subterranean forces at work beneath the desert floor. Yet, starting in 2016, scientists and locals alike began to notice something unprecedented. One of these mud pots began to shift, not by inches, but by hundreds of feet. Over the course of a single year, this enormous column of hot, viscous mud had migrated more than 240 feet across the desert landscape. This movement wasn't random. It was slow, creeping, relentless, like a giant underground organism slowly crawling beneath the surface. As the mud pot shifted, it tore through roads, severed utility lines, and threatened critical infrastructure that supported local communities. Engineers scrambled to assess the damage, and predict where the mud might move next, but the forces driving it were elusive. What made this phenomenon even more baffling was that the mud pot's movement didn't fit typical geothermal patterns. Normally, mud volcanoes stay rooted in place, expanding or contracting in response to pressure changes beneath. But here, entire columns of sludge, gas, and heated water were being displaced sideways, carving new paths and pushing through layers of sediment. Geophysicists posited several theories. Was this a sign of subterranean fluid migration? Could it be linked to changes in underground pressure from tectonic shifts or the rise of magma? Or was it the result of gas pockets inflating like balloons, pushing the mud pot forward? None of the explanations fully accounted for the scale or speed of the migration. What was clear, however, was that the earth beneath Nyland was far from static. It was alive in a way that defied ordinary geological behavior. This creeping mud pot was a visible symptom of the restless forces churning beneath the Salton Sea basin. It signaled an unstable equilibrium, where heat, pressure, and movement combined in unpredictable ways. What had once been a stable geothermal feature was now a moving threat, rewriting the rules of how we understood volcanic and tectonic interactions in this region. Strange brine signatures. Beneath the cracked, sun-baked surface of the Salton Sea region, geothermal power plants had long tapped into the Earth's intense heat, drilling thousands of feet down into subterranean reservoirs of superheated brine. This brine wasn't just hot water, it was a dense, mineral-laden concoction, a seething underground soup that held within it the potential to generate vast amounts of renewable electricity. For decades, engineers carefully extracted this brine, channeling its energy to power turbines and feed the California grid. But starting around 2019, something unusual began to surface, or rather, to be detected in the brine itself. Geochemists analyzing samples from these geothermal wells started to notice anomalous chemical signatures. Most strikingly, the lithium concentrations were extraordinarily high, far surpassing any levels previously recorded, not just locally, but in comparable geothermal systems worldwide. At first, the anomalies were dismissed as outliers, measurement errors, or quirks of sampling. But as drilling expanded deeper, some wells reaching depths of up to 10,000 feet, the data consistently confirmed these elevated lithium levels. The brine chemistry was telling a story nobody expected. Lithium was not a rare guest here. It was abundant, present in concentrations that defied current geological understanding. Even more perplexing was the scale of these readings. Instead of being confined to isolated pockets, the elevated lithium seemed pervasive across the entire geothermal field, extending beyond the active plant sites. It was as if a vast hidden reservoir of lithium-rich brine was coursing beneath the Salton Sea basin, waiting to be discovered. Geologists scratched their heads. The Salton Trough, a tectonic depression riddled with faults and seismic activity, had never been known to harbor lithium deposits of this magnitude. Traditional mining operations typically targeted solid mineral veins or salt flats with evaporative lithium, but here, the lithium was dissolved deep underground in a volatile, superheated fluid, a rare and challenging form to tap, but a blessing nonetheless. The data that changed everything. In early 2023, a seismic shift occurred in the world of clean energy and critical minerals. The U.S. Department of Energy released preliminary findings that sent ripples far beyond California's borders. For years, lithium, the essential element powering the global transition to electric vehicles, grid-scale battery storage, and a cleaner future, had been primarily sourced from foreign countries. But beneath the shimmering, troubled surface of the Salton Sea, California's largest inland lake, lay an untapped treasure, up to 18 million tons of recoverable lithium in geothermal brine. This estimate dwarfed all previous figures, turning what was once dismissed as a barren and toxic expanse into one of the most promising lithium reservoirs on the planet. To put this into perspective, global lithium demand is projected to increase fourfold by 2030, driven by the explosive growth of electric vehicles alone. Every Tesla, Rivian, Ford, and Volkswagen on the road depends on lithium-ion batteries, making lithium an indispensable commodity for the 21st century. Beyond cars, Lithium is the backbone of renewable energy storage, essential for stabilizing solar and wind power on electric grids worldwide. The implications were staggering. Here was a domestic source of lithium, hidden in plain sight, in the heart of the United States, with the potential to reduce dependence on unstable foreign suppliers. It was a historic discovery, the kind that could reshape energy markets, industrial policy, and climate strategy. More than a geological find, it was a turning point in the clean energy revolution, a rare opportunity to position the U.S. as a leader in critical mineral production. And yet, this vast reservoir was located beneath a body of water, long neglected and maligned. The Salton Sea had a history of ecological disaster, polluted runoff, shrinking water levels, toxic dust storms, and dead fish washing ashore. It was a symbol of environmental degradation. Now, paradoxically, it could be the cornerstone of a cleaner future. Scientists and policymakers suddenly saw the Salton Sea not just as a problem, but as a solution, a chance to heal the environment while fueling the green economy. Up until now, the U.S. has been heavily reliant on foreign lithium imports, primarily from South America and China, regions fraught with political uncertainty, environmental concerns, and labor controversies. This discovery signals a seismic shift. America could become the powerhouse of lithium production, dramatically reducing dependency on unstable overseas sources. California Governor Gavin Newsom didn't mince words. He famously dubbed the Salton Sea the Saudi Arabia of lithium, highlighting the mineral's transformative economic potential. What had long been dismissed as an environmental disaster zone, plagued by pollution, receding waters, and toxic dust storms, was now revealed to be a sleeping giant beneath the surface. This revelation sent ripples far beyond California. Investors, policymakers, and industry giants scrambled to recalibrate their strategies. The Salton Sea, once merely a geographic curiosity and an ecological concern, was now a centerpiece in the race to secure the clean energy future. Yet the lithium wasn't just lying in some easily accessible vein. Instead, it was dissolved in superheated geothermal brines, liquid pockets heated by the Earth's magma deep below. Extracting lithium from such brines demanded cutting-edge technology and careful management to avoid destabilizing the fragile underground reservoirs. Scientists and engineers now faced a rare challenge: how to unlock this bounty while preserving the delicate geothermal systems and mitigating environmental risks. The stakes were high. If done right, the Salton Sea could power the next generation of electric vehicles, energy storage systems, and renewable grids. If mishandled, it risked exacerbating an already dire environmental crisis, unleashing pollution, and further damaging the local ecosystem. The world watched with bated breath. The discovery was nothing short of mind-blowing, not only for its scale, but for its potential to rewrite the global lithium map and accelerate the transition to sustainable energy. The only remaining question now was, would they succeed? The challenge of extraction. Despite the excitement, unlocking the Salton Sea's lithium bounty was far from straightforward. The lithium was not stored in solid rock, as in traditional mines, but dissolved in geothermal brine, a complex mineral-rich fluid heated to extreme temperatures thousands of feet underground. Extracting lithium from this type of brine demands cutting-edge engineering and chemical innovation. Unlike conventional mining, which involves blasting rock and crushing ore, the process here begins with deep geothermal wells drilled nearly 2 miles beneath the surface. These wells tap into superheated reservoirs where the brine circulates, heated by the Earth's molten core. The brine itself is a chemical cocktail, saturated with lithium, yes, but also loaded with salts, heavy metals, and other minerals. Simply pumping it to the surface and filtering lithium out is impossible without destabilizing the system. The process involves circulating the hot brine up the wellhead, then using advanced chemical separation technologies, including solvent extraction, selective adsorption, and membrane filtration to isolate lithium ions. These technologies are still evolving and must be refined for large-scale commercial use. But the challenges don't stop there. Once the lithium is extracted, the remaining brine, now chemically altered, must be carefully re-injected back underground. This step is critical to maintain reservoir pressure, prevent land subsidence, and avoid contaminating groundwater or surface ecosystems. Environmental safety is paramount. Any failure in containment could exacerbate the Salton Sea's already precarious ecological balance, leading to disastrous consequences for local communities and wildlife. Engineers and scientists are racing against time to design systems that are not only efficient and economically viable, but also environmentally responsible. Pilot projects are underway to test extraction methods, optimize chemical processes, and monitor impacts in real time. If successful, this project could set a global precedent for sustainable lithium production, turning a once-toxic legacy into a blueprint for circular, low-impact resource extraction. The rewards are enormous. One fully operational lithium extraction facility at the Salton Sea could supply batteries for millions of electric vehicles, accelerate the clean energy transition, and shift geopolitical dynamics by reducing reliance on foreign lithium imports. In a world where clean energy resources are tightly intertwined with national security, economic competitiveness, and climate goals, the Salton Sea's lithium could become a strategic asset of unprecedented importance. But it all hinges on solving these formidable engineering and environmental puzzles, and doing so quickly. Future on the edge. The future, like the Salton Sea itself, remains precariously poised on a razor's edge. Beneath the salty, sulfurous crust of the lake lies a powerful paradox. The very geothermal activity that created the lithium-rich brine also fuels volatile geological processes. The ground shifts, sinks, and releases hazardous gases. Toxic dust storms rise from the drying shoreline, threatening the health of nearby communities already burdened by poverty and limited infrastructure. The environmental toll weighs heavily on residents whose voices have long been marginalized. In this fragile landscape, the race to develop lithium extraction is more than just an industrial venture. It's a high-stakes balancing act between environmental stewardship, economic ambition, and social responsibility. Geopolitics intensify as multinational mining corporations and tech giants pour capital into Imperial County, eager to claim their slice of the lithium bonanza.
Humans aren't the only ones being impacted by chemicals in the sea, as the Salton Sea is an extremely important resource for migrating birds.
These companies lobby hard for fast-track permits, streamlined regulations, and access to federal subsidies. But their arrival ignites fierce opposition from local indigenous tribes, environmental activists, and community leaders who have endured decades of neglect and ecological harm. Tribal governments demand that their rights, land sovereignty, and cultural heritage be respected, refusing to be sidelined in decisions that impact sacred lands. Environmentalists warn against reckless drilling practices that could contaminate precious groundwater supplies or trigger seismic events with devastating consequences. The community calls for transparency, fair compensation, and meaningful inclusion in every step of the process. On the technology front, researchers and engineers are sprinting to innovate. Traditional lithium mining techniques simply won't cut it here. Instead, they must pioneer advanced geothermal lithium extraction methods that can capture lithium efficiently while re-injecting depleted brine to maintain underground pressure and prevent land subsidence. Some of the most promising approaches involve direct lithium extraction, DLE, technologies, which use chemical absorbents or membranes to selectively isolate lithium from brine, drastically reducing water use and waste compared to evaporation ponds. But scaling these methods commercially is still an open challenge, requiring unprecedented collaboration between science, industry, and local stakeholders.
One of the environmental challenges out here is the Salton Sea and some of the contaminants and some of the public health.
The clock is ticking. The Salton Sea's surface continues to shrink, its waters retreating inch by inch each year, exposing more toxic sediment and worsening dust pollution. This environmental decline only increases pressure on stakeholders to act swiftly, but with caution. In this high-stakes drama, every decision will echo for generations. The Salton Sea is no longer just a forgotten wasteland. It's a crucible of competing interests and a test case for how the world balances urgent climate goals with responsible resource management. Because buried deep beneath that cracked, toxic crust lies the key to a cleaner, faster, electric tomorrow. A future powered by a historic discovery the world never saw coming. The lithium frontier is here, and everything depends on how we handle it. Do you think the Salton Sea's lithium discovery will change the world or spark new conflict over its control? Share your thoughts in the comments. Thank you for watching this video with us, and catch you in the next one.